Good morning, good afternoon, everyone, and welcome to today's webinar. First, I would like to share my screen. Let's see, I hope everything goes okay. You can see my screen now? Can you confirm to me?
Yes, we can see your screen.
Okay, perfect, thank you. Welcome, everyone. As usual, my name is Carmen Gruta. I'm your host from Technovis Crystallization Systems, and today we are thankful to our presenters from JSTAR Research that made this webinar possible and available to all of you. Effective investigation of crystallization kinetics for process design and control of polymorphic systems. Today we have with us Diana and Weiqi, and I will introduce to you our presenters today in a while. Just before that, I have a few details to share with you, technical details. You still see my slides, right? The webinar is being recorded, and the recording will be made available to you most probably tomorrow, to all of you, to all the attendees, and also we will send a link to those that they are not with us today present at this webinar. It will last about 30-45 minutes, I think, including questions, and tomorrow you will also receive an email from us with access on our website and on the YouTube channel, and most probably also maybe in the coming days from JSTAR with more information. If you have any questions to our presenters today or to us, to text, please feel free to use the chat question feature of this webinar. Ask, and at the end of the presentation, this webinar, we will take your questions and we will try to answer them as much as possible. Or after the webinar, if you think that you still have a question, you'd like to understand something, don't hesitate and write either to us, to Technovis at info@crystallizationsystems.com, or directly to our speakers. I'm pretty sure they will also share their contact details with you. Just before we start, a little bit about Technovis, who we are, who are we. For those that they do not know Technovis, we are on the market since 2005, and we are active globally. We have currently three products in our product portfolio: the Crystal Breeder, Crystal 16, and the crystalline instruments. And stay tuned, because in end of this year or early beginning of next year, we are coming with a new product portfolio and a fourth product for us, which we are very excited to present it soon to you guys. A little bit, I've seen a few of the names that join us today, and I am pretty sure that some of you already know the Crystal 16 or the crystalline, or both of them actually. For those that do not know or have worked in the past with our instruments, please remember the Crystal 16, the one that you have here in the middle. The multiple reactor system with 16 reactors working at 1 milliliter scale is your instrument for solubility, temperature dependent solubility determination, metastable zone width, solid state screening, induction time measurements, nucleation rate, and so on. And the crystalline is with the camera technology, or if you have a Raman spectrometer in your lab, you can also connect it to this instrument. It's your instrument to be used in development when you develop your crystallization process or optimize this process, or even in formulation. The Crystal Breeder is more the instrument with all its gadgets, how I like to call it, with evaporation, vapor diffusion, helps you to grow single crystals. If you are busy with that, or you want to grow single crystals, Crystal Breeder is your instrument for that. And this is about Technovis and our instruments. Now come to our presenters of the day, and I will not take that much time, but I would like to thank you guys once again for making this possible. And not only to you, but also to Jian Wang, that she always was an advocate of excellent science and made it also possible, starting the discussions about the joint collaboration between Technobiz and JSTAR. And with you today, we have Dr. Diana Camacho Corzo, Senior Research Scientist at JSTAR, Scientist in Crystallization Process Development Group at JSTAR Porton Company. A part of this group, she has focused on implementing methodologies for understanding crystallization kinetics at early stage of crystallization process development. Diana earned her PhD in chemical engineering from the University of Leeds in UK, where she also was a postdoc implementing modeling tools for crystallization process design and scale up. And I think part of that research we also will see today, if I'm not wrong. And our first speaker of the day is Weiqi Chen. He is also a senior scientist at JSTAR with experience in early phase crystallization process development in the crystallization group of JSTAR. He specializes in applying process analytical technologies, so PATS tools in crystallization process development for enhancing process understanding. His experience in automated systems, particle engineering, and scale up and technology transfer. Prior to joining JSTAR, he was a postdoc at University of Delaware, and he earned his PhD degree at New York University, and also with a master from the University of Florida. Oh, many nice cities, I must say. And with a bachelor in science from Nankai University. So these are our presenters today. Once again, thank you for making this possible. I will stop sharing and I would allow you to share. I will make you also oh, you are a presenter already, I think.
Yes. So
and now you can actually.
Let me try. Can everyone see my screen?
Yes, and now it's in presentation mode. Perfect.
All right. Yeah. Okay, great. Thank you, Carmen, for a kind introduction. And hi, everyone. This is Weiqi Chen. Today, Diana and I will introduce two methodology to effectively investigation of like crystallization kinetics. And we're going to show how we can obtain high quality data and how we can, from this data, we can get the critical process information and how we use that information to design a process to isolate the pure target form, which could be challenging to isolate otherwise. So first, a brief introduction about crystallization group at JSTAR. At JSTAR, the crystallization group is serving as a bridge to fill in the gap between the API synthesis and API formulations. There are four areas that we're mainly focusing on, which are the solid form discovery and studies, crystallization process developments, pre-formulation evaluations, particle engineering, and co-processing. And besides experimental methods, we also have computational tools and experts in-house to support us the R&D throughout these all four areas. And it's a highly integrated department, and we use synergistically developments. And one thing that we understand and we highly value is the efficiency of the development process. As we know, like the crystallization process development could be labor intense and time consuming. And here at JSTAR, we are fully equipped with a highly automatic crystallizers from different scale to cover different scope of works. For example, from the scouting scale, we have temperature control shaker, and we also have two crystalline systems, which needless to introduce. The these are very nice systems where we can get high quality in situ data. Actually, in today's talk, one of the methodology we introduce is using this system to obtain the nucleation kinetic data, which we will talk about later. And on a slightly size up, we have the EasyMax reactors. These reactors are right now commonly used and in the industry, and these are highly automatic reactors. And on a slightly size further, we have 1 liter reactors like Atlantis or Optimax, and also for larger scale, we have 2 liter, 5 liters, up to 100 liters. So for 100 liter reactors, we have RX10 controller from methodologies as well to have the highly automatic operations. So all this highly automatic crystallizer, we enable us to get the run as much experiments as possible in short period of time by running them in parallel. In the meanwhile, we also wanted to get maximum information from each process. By doing so, we're using the process analytic technology, also called the PAT tools. And especially one of the most advanced one is the Blaze matrix, where you can get in situ microscope image and also PSC profile. In the meanwhile, you can integrate with a Raman to provide information about polymorphisms. Actually, and today, the other methodology we introduced, we're using this system to get the data about the form conversion kinetics and then get the critical information about the process. So besides that, we also have like pro-based Raman systems and also FBRM and AIR to provide information such as PSC profile or the concentration of your compound, for instance. So this maximizes efficiency, also in-depth understanding of the crystallization systems will really enable us to be right at first time to facilitate this idea of quality by design. And at the end of the crystallization R&D work, we'll strive to have a robust and efficient crystallization process to obtain the product that meets your critical product quality attributes. And these attributes can be including such as chemical purity, physical stability, polymorph stability, particle attribute, such as morphology, flow properties, and also residual solvent levels or solid form purity. So in today's example, we're going to talking about a system, how we can isolate pure target form, which is related to the solid form purities. So, all right, so this is the system I'm going to introduce today. And it's a compound with 2 forms in interest, form 1 and form 2. And sure if I can share a pointer.
Yeah.
And yeah, okay. So here's the solubility profile of these 2 forms at different temperatures. At the first glance, you will see that the solubility, they are very close to each other throughout the different temperatures. And I think they are within the experimental errors. And then this indicates that you will see that they are hard to isolate it. And actually, this is quite common in the industry as well. And to design a process that could be for isolate the pure target form, there are at least 4 critical questions that we need to answer before we even approaching to design the process. First is that, is this an enantiotropic system or is it a monotropic system? If it's enantiotropic, then what would be the transition temperature? And what about the form conversion kinetics? Right, for the third questions, I encourage you to start thinking about this. If you have to design a form conversion process, at where you would want to do it, at lower temperature or at a higher temperature, and why is that? We're going to reveal the answer to these questions in few slides, but I encourage you to start thinking about these questions. And the last but not least is what about the nucleation kinetics look like? And if one wanted to design a nucleation dominate process, and how could he or she gonna do it? All right. So as we mentioned, we're gonna introduce two methodology, and I'm gonna start with the first. It's a form conversion kinetic assessment. So at the end of this study, we're gonna get information such as transition temperature determination and optimum conversion temperature determinations. And later, Diana would introduce a second methodology, which is the nucleation kinetic assessments. And at the end, we can get the mapping of polymorph behaviors and also the cooling rate for isolation of target polymorph. All right, so for the first methodology, as we mentioned before, we are using the Blaze integrate with a Raman spectroscopy, and we are doing our experiment in the EasyMax systems. So these two forms can be differentiated by their characteristic peak in the Raman spectroscopy. And for these experiments, what we do is we prepare the saturated solution at the testing temperatures, and then we add the equal mass amount of both form into the system. Then we use the Raman to tracking the conversion kinetic isothermally. And here's an example of where we're starting over both form 1 and form 2. And over time, in this case, you see the form 1 is converted to form 2. All right, so now we have the methodology, but there's one thing that you need to pay special attention to before you measure the data. Otherwise, your data could be misleading, which is the impact of the particle size. So here, what happened is that it's for example, from form 1 to form 2 conversion, it's a solvent-mediated form conversion process, and it's a two-step process. What happened is the form 1 to dissolve first, to be a dissolved compound, and then it crystallizes out to be the other form, in this case, form 2. And it's a two-step process, and either step could be the rate determined step. So, and in the meanwhile, as we know that the dissolution is a surface phenomena, meaning that if you have a higher surface area, you can have a higher dissolution rate. And in this case, since we're more interested in the intrinsic crystallization kinetics, so we are intended to have where that the crystallization kinetic would be the rate determining step. By doing so, you can just decreasing the particle size. Because we know the smaller particle size, you would have a larger surface, specific surface area. And here's an example of how this particle size is going to impact your results. So here's an experiment we run it at 40 degrees C with a large particle and a small particle. You see when you use the larger particles, the time to convert it to the other form could take almost 4 times longer than when you use the small particles. And when you repeat the same process at the 50 degrees C, and you see the similar phenomena. However, something also important here is that if you notice that if it's larger particles, it would appear that the 50 degrees C, that the conversion would be faster than the 40 degrees C. That is only because the dissolution rate is higher at the higher temperatures. However, in truth, is the intrinsic kinetic is that the 40 degrees C actually have a higher conversion rate than the 50 degrees C. We will tell you why is that in the next slides. But here I just wanted to emphasize that if you don't design the experiment properly, you could get the misleading data for your systems. So now we have the methodology and we know how to get a high quality data. Then we go ahead and measure this kinetic data at the 5 different temperatures. And then by extrapolate the conversion, and we know for sure that the transition temperature is about 56 degrees C. Then we run the experiments again at 58 degrees C to confirm the results. Right. So now we know that it's an enantiotropic system with a transition temperature about 50 degrees C. And there's another interesting phenomenon I would point out here is that there is an optimum conversion kinetics between 40 to 45 degrees C. So it's either lower too low temperature or too high temperature. And why is that? That it is because when you're increasing your temperature, yes, you are increasing the kinetics of your crystallization. However, in the meanwhile, you're decreasing the driving force for this form conversion. So because of these two effects, you are ending up at optimum conversion kinetics somewhere between in this case, 40 to 45 C. All right, so for based on this information, we can start our design for the process. For example, in this case, Form 2 isolation would be easier since it's the more stable at a lower temperature. Now we know you have to be crystallization below 56 degrees C. And we also know it has efficient form conversion at 40 to 45 degrees C. If you ever need to design a form conversion process, and then you know what temperature you're going to. And also if, for example, in the process where you have end up in the mixed form, and you don't have to start over your process, and you can just effectively convert it to Form 2 at 40 to 45 degrees C in this case. And we can also design for Form 1 isolation. In this case, we can design somewhere above 56 degrees C in this case. And we can also do hot isolations for the systems. And I would say this is not impossible in the reality. It can be achieved, but there's implication about this process. For example, you have to control the temperature very well. Otherwise, you run into the risk of crushing out the other form, the Form 2. And also the hot isolation, meaning that you probably have to do hot wash that you can lead to high yield loss. So which is also undesired. And Diana will introduce another method that can actually isolate this form under the room temperatures. And to sum up my part, and we answer the first 3 questions. And we know now it's an enantiotropic system because its transition temperature is much lower than its melting temperature. And we also determine what's the conversion kinetic look like, and it enable us to control and efficiently form conversion for either form isolation, and it can reduce the cycle time for your process. Now I'm going to switch the floor to Diana. She's going to talk about the nucleation kinetics for the system. All right, Diana.
Okay. Good morning, everyone. So far from Weiqi's presentation, we have seen that Form 1 is the metastable form in this specific case. However, we have also seen that the thermodynamic difference between the two polymorphs is not significant. And from conversion kinetics, we saw that there is a very narrow space in which the crystallization of the metastable Form 1 is favored. And in this space, the conversion takes place at very high temperature and at a relatively low conversion rate. So what additional information can we collect that help us into designing a crystallization process to isolate optimally the metastable form? So for this specific case scenario, we apply a second methodology to perform an assessment on nucleation kinetics. And out of that assessment, we were able to obtain something that we call a mapping of the polymorphic behavior and establish a cooling rate for isolation of the target of either of the two polymorphs as well. So I am aware that many of the people on the audience would have heard about the methodologies that are available to collect experimental data with the aim of assessing nucleation kinetics. But I'm going to just provide at a very high level description for those who are not familiar with them. So there are well-known methodologies. One is the isothermal method, and the other one is the polythermal method. In the isothermal method, what is done is that starting from a specific solution concentration, one crash cool that solution up to a certain level of supersaturation and measure the corresponding induction times. If a sufficient range of supersaturation is chosen, then by applying classical nucleation theory, one can work out parameters such as interface tensions and then also the corresponding nucleation rates. On the other hand, we have the polythermal method. This is very simple. It's nothing else that collecting the corresponding crystallization temperatures as a function of cooling rate. So for instance, if we have for a given solution concentration, if we apply a thermal profile, we can collect the trend of the crystallization temperature and the dissolution temperature as a function of cooling rates. For the specific case study that we are presenting today, we chose this polythermal method mainly for two reasons. One is because we think that the polythermal method is more practically aligned with the design of batch cooling crystallization. And also because for the analysis of the data that are collected via the polythermal methodology, there are a range of models that can be used to obtain nucleation kinetics parameters that are not only limited to classical nucleation theory, but that range from very empirical one to first principle based models. So how do we collect the polythermal data? So in order to collect the polythermal data, we use the crystalline, which is an equipment from Technobyte, our host today. I am sure that, as Carmen mentioned at the beginning, that many of you are familiar with this equipment. And in general, the crystalline offers a setup in which you can run 8 different experiments at the same time by placing solutions that can range between 2 milliliters up to approximately 7 milliliters in this type of reactors that can be agitated by impellers with different designs. These reactors can be independently set up to run specific thermal profiles. And 2 different types of data can be collected out of these experiments: the traditional turbidimetric profiles that will show you the clear and cloud points. But what is interesting specifically for this case study is that you can also collect in situ images that will allow you to establish more accurately, especially the crystallization points, and at the same time monitor what happened with the transformation between one polymorph to the other upon the cooling and heating cycles via changes in morphology that you can see through the in situ images. Okay, so 4 different concentrations were selected for this study. And 5 different cooling rates were applied to each of those concentrations that were selected. Due to the stochastic nature of nucleation, then several repeats were done at each of the concentration and selected cooling rates in order to obtain average temperatures of the crystallization points. And in addition to using the in situ images provided by crystalline, we also isolated the solids at the end of each of the thermal profile and subjected them to FRPD analysis in order to validate what was the corresponding polymorph that we were crystallizing under a specific set of conditions. So in the end, we obtain a very useful mapping of what we call the polymorphic behavior. For you to understand exactly how these data points are plotted in this graph, I'm going to give you a couple of examples. So if we take a specific concentration, in this case, solution concentration, in this case, 8.2 milligrams per milliliters, which will be located in this region. upon using different cooling rates starting from the solubility, we will see that the temperature at which the crystallization will take place is changing as a function of the cooling rate, and the polymorph that is being crystallized depends on which one of the cooling rates was applied for that specific concentration. On the other hand, if we look at a single cooling rate, for instance, 0.5, which will be located around this region, then we will see that as the concentration decreases, the temperature at which crystallization takes place will be different, and the polymorph that is being crystallized is a specific polymorph via the assessments of XRPD or in situ images. So in the end, we obtain a very useful, powerful tool that is showing the regions in which nucleation will be favoring the crystallization of either of the two forms. As you see from this analysis, we have a wider space for nucleating form 1 in contrast to the stable form 2. And what is this mapping is also telling us is that the form 2 will be favored when we start with high solution concentration and we cool that solution at the slow cooling rates, as you see here represented by the blue dots. So in many cases for the design at early stage of crystallization process development, a map such as this one will be enough to design processes to isolate either of the two forms. But in some cases, additional information related to nucleation kinetics would need to be obtained, especially when one is performing optimization of that crystallization process. Although I am aware that this is not the aim of the talk to introduce you into the detail of the models that are available to obtain additional nucleation kinetic data, I just want to make you aware that, as I mentioned before, there are a number of different models that range from very simple semi-empirical approaches to first principle-based approaches that can be used to further analyze the polythermal data and obtain nucleation parameters. The most widely used and the simplest to use is the Nibel approach, which I'm sure that many in the audience would have already used before. And that approach was used for this specific case that we are presenting today, but you can also use more first principle based approaches, such as the one called KB-HR approach, which we also apply to the data points collected experimentally, in which you can not only make like a high level comparison between the nucleation rate of different systems and the different conditions, but you can also get a more physical insight into the nucleation pathway by identifying what if the nucleation is taking place via instantaneous of progressive nucleation, and by calculating parameters which have physical significance, such as the interfacial tensions and their corresponding nucleation rates. For those of you who might be interested in learning a little bit more about the different models that are available in the literature, there was a paper recently published in Crystal Grow and Design that presents a very useful review, not only in the methodologies that are available for collecting the data, but also in the models that you can apply with the advantages and disadvantages that this represents. So this is a summary for you to see specifically the type of data that you can get by applying either empirical or first principles based approach. So if you apply the Nibel approach, for instance, which is based in this very simple power law, one can get values for what is called the nucleation order, in this case, as a function of a specific parameter, in this case, concentration. And as well, one can get the nucleation kinetics in terms of the mass that is being crystallized per unit volume per unit time. If, on the other hand, we apply more first principle based approaches, then in addition to being able to establish the nucleation pathway that your system is following, we can also obtain the nucleation rates in terms of the amount of nuclei that are being crystallized per unit volume, per unit time, but with an added usefulness, which is that these nucleation rates can be calculated as a function of a specific supersaturation level or metastability level. So with all this information in hand, we now have been able to answer to the questions that we stated at the beginning of the research. We have established that this is an enantiotropic system, that the transition temperature is 56 degrees C. But in addition to that, we have been able to collect very fundamental data that would allow us to design a crystallization process from the concept of quality by design, because to isolate either of the two forms. So what follows is an example. We were able to design a crystallization process at the multigram scale for the isolation of 4,1 from solution by using mainly the nucleation kinetic data that we collected. So this process was an unseeded crystallization, cooling crystallization process, starting from the solubility by cooling at the suitable cooling rate that will allow us only not to obtain the pure form 1, but also to optimize the crystallization rate for the obtention of this specific polymorph, which was a cooling rate of 0.3 degrees C per minute. On a second instance, using as well the set of data that we presented via the first methodology, we were able to isolate the stable polymorph form 2 from solution, but this time using seeded cooled crystallization. So with this map, after seeding, we were able to optimize the crystallization rate at which we were isolating the stable polymorph by aging the solution at a suitable temperature, corresponding temperature. So I hope that we hope that through the presentation we were able to show you that if one collects fundamental data from the very beginning of designing a crystallization process, one should be able to design a crystallization that allows you to isolate either of the two polymorphs based on specific particles attributes that you might be targeting. So with this, we come to the end of our presentation. I want to acknowledge my colleagues at JSTAR, Chen-Yu Lu, Abhinav Karwani, and Dr. Jian Wan, who supported this research by supporting the collection of experimental data and useful discussions. And with this, we are open for the discussion with the audience.
Thank you very much, Diana and Weiqi. And as I also mentioned in the very beginning of this webinar, thank you, Jian, once again for making this possible and initiating the collaboration, and to your colleagues that contributed to this work. I do see a raised hand. Please do make use of the chat or Q&A function of this webinar. Because all the attendees are in listen-only mode, so that's something that I cannot change during the recording. Before we go further, Diana, you have mentioned something quite interesting, that today you are presenting a case study where the polythermal method worked well. And it is really nice to see how it is really a combination of all the PAT tools, all the vendors available on the market, the combination of our instruments and how you go from the smaller scale to larger scale to see the metal reactors that you see always in the labs, and also even I recognize some of the pictures from Blaze Metrics that you have shared. Are there cases where you had to use, or how do you decide which method to use, the polythermal or the isothermal one? How do you take your decision for later stage?
So as I mentioned, I mean, either of the two methodologies will give you sort of a similar sort type of parameters based on classical nucleation theory. But from my point of view, from my experience using the polythermal methodology is more practically, because when you are designing batch crystallization, usually it involves some sort of cooling crystallization during the process. And this methodology is more aligned with the design of this type of crystallization. So since the very beginning, in addition to collecting the nucleation kinetic parameters, you are getting more of an insight of what can happen within the crystallizer as you apply a given thermal profile.
We did receive another question: how to determine nucleation rate if the compound changes the form during the cooling while using polythermal method?
Yeah, that's a good question. Yeah. So that is the reason why I think both the combination of the in situ images provided by crystalline and the fact that we validated the form that we were being crystallized at the end of the application of this specific thermal profile will allow us to establish what part of the data can be used to calculate nucleation kinetics for one form or the other. Yeah, so once you apply the thermal profile, you know, I crystallize here form 1 or form 2, and then you have to sort of separate those data and apply a given model to that specific set of data, which will target the specific nucleation kinetics of one of the two polymorphs.
Another question I see here, there is any way to capture effect of changing, mixing, and or vessel geometry impact in metastable zone weight and nucleation kinetics?
Yeah, well, that is something that it has to do more with optimization and scaling up of the process in some sense. Yeah. So ideally, we know that the nucleation kinetics is influenced by two parameters, to say it in a way, thermodynamics and kinetics. So the thermodynamics sort of should be stable for all of the scales and regardless of the operating parameters that you are using. But the kinetics is going to change as well, depending on the hydrodynamics of your systems, which will change based on a scale or based on impeller speed of the geometry that you are using. But for that, as well from my experience, what I have done in the past is there are two things that can be done. One is that you can extrapolate this methodology to different specific scales of reactors, so sort of repeat the same profiles, at least for a couple of geometries or scales more, and try to work out some sort of correlation for that specific case. But on the other hand, so, what people is doing at the moment is that is using these specific methodologies that can be done at the smaller scale to collect the fundamental parameters that can be, for instance, used within population balance models. That then you can sort of combine with softwares that can provide you more correlation between the effect of the hydrodynamics on nucleation or growth kinetics. Yes. But yeah, of course the kinetics is specifically for a given system and specifically for a given reactor scale.
Yes.
So it could be like a balance.
Yeah. per compounders. Yeah, indeed, I do agree with you, Diana. Besides the many thanks that we received there, it's somebody that says, very nice presentation as well. I'm a user of the Crystal 16 actually, and says that I am using the Crystal 16 just for solubility measurements. Oh, it's a pity, only for that. I haven't done these experiments to investigate nucleation rate. Does it make sense to investigate the nucleation rate also just for one known polymorph? Or in other words, should I always do this? Well, I think you guys know also the Crystal 16, right, Diana?
Yes.
You also have it.
Yeah.
At least the newest Crystal 16, but also with the older one, facilitates this, and even it can be easily the data extrapolated from the software, from the multi-analysis feature of the new software of the Crystal 16 launched last year. I don't know if you want to add something here.
Yeah, well, many of the audience also would be aware that there is a way of obtaining solubilities that are not based on gravimetric techniques or applying LC, but you can also obtain solubilities based on the application of this polythermal methodology, which is the way I imagine the person who asked the question is doing. So if you, for example, apply this polythermal profile, not only for a single concentration, but for different starting solution concentrations, and you apply those thermal profiles to obtain both the onset of dissolution and onset of crystallization, then by extrapolating of the dissolution temperature lines to the y-axis, you can obtain the solubility, and at the same time, by extrapolating the crystallization temperature lines to the y-axis, you can obtain also the supersaturation or supersolubility. So you will have already there the data that you will need both for solubility and for assessments of nucleation kinetics.
Yeah. Another question would be, how would you perform polymorph mapping for an anti-solvent crystallization?
Yeah. Yeah, so we have thought about that, and then I think what it could be done is that the polythermal methodology would have to be applied for different solution concentrations at a specific mixture of the solvent and anti-solvent. So you will have to repeat the polythermal methodology for, I don't know, 100% solvent, 50-50, 70-30, and you can do the mapping by applying that polythermal methodology for a specific combination of solvent and anti-solvent.
And one last question, because I see that we went also far with the timing. Can seeding lead to the crystallization of a desired form, irrespective of the crystallization rate and temperature and solvent system? So without thinking of the crystallization rates or the cooling rates or the temperature that you are using or the solvent system, just by seeding, can you form the form that you would like to form?
For this specific case, maybe you actually can answer that question.
Yeah, I can answer the question. Yeah, in this case, we wasn't able to, just by external seeding. There's two factors in this. One is that when you seed it, especially for like a foam 2 crystallization, which, let me see, which is like stable at lower temperatures. And we see we need to seed it below transition temperature, where is 56 degrees C. And if we want to start with like a clear solution, you have to also with a decent amount of the volume efficiency, and you have to seed it at a very high, kind of a high supersaturation ratio. In this case, for example, 1.6. And then we do see that when you seed that, it sometimes can also trigger secondary nucleation, or like a trigger nucleation of the kinetic favor form. In this case, for example, like form 1 could be triggered. That's why like we do a form conversion at like aging points at 43 degrees C to de-risk so you confirm that you convert this form to the other form. So we have tried just external seeding itself, and itself doesn't work, not as robust, we would say. At the end, you will always get some mixed form.
Okay, thank you. I see two more questions. I will try to answer them fast. Somebody is asking about the integration of a tornado Raman into the crystalline and measuring the in situ the transformation. I'm not very sure if you guys at JSTAR have this, but I am aware of several customers of ours that they have this this integration of the tornado Raman into the crystalline. And we also have two application notes where we show the use of the Raman from tornado and following the polymorphic transformations while you are performing the experiments. So yes, Nelson, it is possible on our website, or I can share afterwards an application note with you. And then another user of the crystalline has questions related to the clear and cloud point. If you are a user of the crystalline instrument, I'm telling you, use the images to determine the clear and cloud point. The image tends to capture 1 second faster or a few seconds faster or more accurate the clear and the cloud point, and it has everything to do with the length path between the source and the detector. I will not get too much into details there. It is a different story for the Crystal 16, where the path is really ideal. It's smaller, but if you have a crystalline, use the images. And the crystalline version 2, which we launched end of last year, has this feature already integrated in the software, and it's a very easy, a few clicks, you can extrapolate or extract this data out of the images. The software does it already for you. If you need more information, let us know, and we can send an application note or more information. So questions are coming and coming and coming, but we need to stop. Sorry for this. Thank you very much, both. I haven't asked you up to now if you are allowed to share the slide. I also see a few questions if the slides can be shared. If you are allowed to share the slides, please send them in a PDF format to us, and we will make them available on our website. Once again, Diana, Weiqi, Jian, thank you very much for bringing this topic today, making it available to everyone. Have a good still day. Good afternoon and evening to Europe, and hope to see you soon at our next webinar. Thank you. Bye.
Thank you very much, Carmen. Thank you, everyone, for joining. Thank you.